So let's talk about the one derivation that you might actually need to use, which would be the derivation for a long, thin rod. Okay, so we'd start out with our integral for I. I'm going to draw a picture first, actually. So we're going to derive value for I if the long, thin rod rotates about its center of mass, the position of the center of mass. So I at the center of mass, we know we need to integrate r squared in terms of dm. So the whole length of this rod is length L, and it has a mass of m. So we need to relate the entire length and the entire mass to the mass and length of some very tiny, infinitesimally small sliver. And we're going to sum that over the entire length. So if it's a long and thin rod, we can ignore the volume. So volume is negligible. And surface area is negligible because it says it's long and thin. We need to focus on the linear mass density. We know that linear mass density is lambda. That's equal to the mass of the entire object divided by its length. We need an expression for the whole mass over the whole length compared to the linear mass density of just this tiny slither, dm, with radius or length of dr, some really, really small length. Okay, we're going to relate it. We're going to take a look at just half the rod first. Sum from 0 to the end. And we're going to have to multiply that integral by 2. So because this is symmetrical, right? So if we were to actually cut this in half, from the center of mass to the end of the rod on the right-hand side versus the center of mass to the end of the rod on the left-hand side, they are symmetrical. So they have the same amount of mass, the same amount of length. Okay, so we're going to relate that little slither of dm to the little length dr. And we need to plug in to replace dm to get it in terms of dr. So I'm going to cross multiply here. So I'm going to have m dr is equal to dm times L. I want dm by itself, so I'm going to divide both sides by L. I have that dm equals m over L divided by dr. So basically what this expression tells us is that the mass of this little slither is equal to the total mass of the rod divided by the total length of the rod if we were to take the integral in respect to dr. Okay, so we're coming up with a relationship to relate total mass, total length to the mass and length of that tiny little slither. And then we plug in. So you have the integral of r squared. For dm, we're going to plug in m over l dr in its place. We know that the entire mass and the entire length of the rod will stay constant, so we're going to move that in front of the integral. We're technically going to integrate from this position of 0 to 1/2 L. So if our bounds of integration are from 0 to 1/2 L, we're going to need to multiply the entire integral by 2. Or we can do a second integral in which we then integrate from 0 to negative 1/2 L. But it's easier to just multiply the entire equation by 2 to take care of that symmetry. So I have 2m over L. I'm going to integrate r squared dr from 0 to 1/2 L. Okay, so now here's the easy part. When we integrate r squared in terms of dr, what expression will we get? Guys?
Is it 1/3 r cubed?
Right, 1/3 r cubed, and we're going to plug in 0 to 1/2 L as our upper and lower bounds. When we plug in 0, the equation will simplify to minus 0. So I'm going to have 1/3. I need to cube 1/2 L. So when I cube 1/2, right, I get 1/8 L cubed. Or, yes, L cubed, there we go. And then technically minus 0. So when I simplify here, where'd you go away? There we go. The 2 will cancel. This will become a 4. 3 times 4, I get 12. One of my L's will cancel. Okay, and I still have my M. So my equation is 1/12 ml squared. Okay, and if you take a look back at your notes, right, that's the exact value for I of a long, thin rod. Okay, questions so far? No?
Nope.
All right. So this took a little bit longer than I expected. It's really difficult to write on here. So what I'm going to do is, I think this was the right document. Here we go. So there are equations that relate linear to rotational velocity acceleration. And constant angular acceleration. So I'm going to post this information up here, this little chart. Okay, I'm going to start with the torque equals I times alpha equation. Okay, so I think that if you guys review this stuff by yourself, what is angular velocity, angular acceleration, uniform angular acceleration, you guys will be able to figure that out. Okay, so I'm not going to waste time talking about that. I'll just post these equations up here in Classroom, but I'm going to start with the rotational equivalent of Newton's second law. Okay, so torque is a force at a radius that causes rotation. It's measured in Newton meters. Okay, we just spoke about I. I'm not going to retype that. We know that Newton's second law equivalent for rotation, so we have F equals ma, would be torque equals I times alpha. When we assign direction, if the force is in the direction of rotation, we assume that it's positive, with the torque rather. If it opposes the direction of rotation, we say that it is negative. All right, so let's talk about some common equations or situations in which we might see on the AP exam and write down those shortcut equations. So when we have a pulley with mass, and M1 is greater than M2, let's say this one's M1. Right, we start out with torque equals I times alpha. Okay, both forces are at a distance r from the axis of rotation, which would be the position of the center of mass. Okay, if M2 is smaller, when we release the pulley, which way will M2 accelerate, up or down?
Up.
Up, okay? So if it accelerates up, and this tension is technically pointing down, it's going to oppose the direction of rotation. So it's going to rotate in this direction, which is technically counterclockwise. The force of tension, T2, points opposite to the direction of rotation, so it's going to be negative. And T2 occurs at a radius r from the axis of rotation. Mass 1 is going to cause that rotation in the counterclockwise direction. So T1 is going to be positive. And that occurs at a radius r. So the torque due to tension 1 will be positive. The torque due to tension 2 will be negative. So the net torque would be tau 1 minus tau 2 equals I. The moment of inertia of a disk or a pulley is 1/2 mr squared. Anyone remember what we plug in for alpha?
Is it V over R?
So you're thinking of v squared. You're thinking of tangential velocity squared over the radius. We use that for uniform circular motion. It's technically here, right, we relate alpha to our radius. Should use a capital R here. So you plug in A over R. Remember these two equations here? The linear acceleration or translational acceleration is equal to the angular acceleration times the radius. Okay, tangential velocity or the translational velocity would be angular speed times the radius. In uniform circular motion, when there is no angular acceleration, we can use that relationship that the tangential velocity squared divided by the radius would equal A. That's only when alpha is 0. We can use that. So there's only, we plug that in for centripetal acceleration. Which is constant with UCM. I can't write the word constant, I don't have enough room. I'll just write it over here. So I'm going to plug in A over R for alpha. Okay, we can see here immediately that one of the R's will cancel. I'm going to plug in the relationship for tau 1, which would be tension 1 at a radius R, minus tension 2 at a radius of R, equals 1/2 m times R times A. All of our radii would cancel when we divide both sides by the radius. So we have an equation for the linear acceleration in terms of the two tensions, mass, which should be a constant, and acceleration. To get acceleration in terms of all fundamental constants, we use Newton's second law in terms of linear values, which would be F equals ma. We do it for both objects, for M1 and M2. So for mass 1, when we sum the forces in the y, okay, we technically have T1 minus M1G equals M1 times A. Do you want me to show the work for that, guys?
I'm good.
Okay. For object 2, I have negative T2 plus M2G, right? Technically, because it should accelerate down, down would be positive. This one should accelerate up, so up is positive. We solve for T1 and T2. We plug in using a system of equations. Man, this is frustrating that this keeps happening. There we go. So we solve T1 over here. We get, when we solve for T2, we get M2G minus M2A. We add T2 to the other side, subtract M2A over. Then we plug these in back into our equation for the rotational equivalent. And then we solve for A. And remember that this is the mass of the pulley. We have to distribute that negative sign. I should probably do this to make sure. Something feels wrong. Hold on. Something's wrong. Where's my notebook? Should be M2. Oh, you know what I did? I made a sign mistake all the way back here. I reversed the signs. Oh, okay. So I tried to do this faster because we were running out of time, and I made a sign mistake by trying to do that. So M1 is heavier than M2, so it's going to accelerate down. So down is positive in terms of Newton's linear version of the second law. Okay, so that means that force of gravity should be positive, tension should be negative. So when we solve for tension here, T1 equals negative M1A plus M1 times G. T2, because M2 is smaller, it should accelerate up, so up should be positive, which means that T2 would be positive, and the force of gravity would be negative. So when we solve for T2, we get M2G plus M2A. So when we plug in, we have negative M1A plus M1G minus M2G minus M2A. So then when we solve, right, we have to add M2A and M1A to the other side of the equation. We factor out an A and we divide. So you get 1/2 the mass of the pulley plus M1 plus M2 in our denominator. And our numerator becomes M1 minus M2 times the quantity J. Okay, so that's our shortcut equation for an Atwood machine with mass. Okay, so how are you feeling? You guys want to keep going?
I have to go because it's Bree's birthday, so I just have to.
Okay,
I don't know.
that's totally fine. I appreciate you showing up, and I will post the rest of the notes that we did not get to Classroom.
Okay, thank you, Miss O'Connell.
No problem. Have a nice day.
Yeah.
Can I just ask a few questions on like the actual exam?
Sure.
Like, because I'm trying to think of like what I should have with me for the exam. So obviously like note card with all the equations, and then like maybe some examples problems that we've done.
Okay,
different
yeah.
types of
Do you
problems
have
I'm not comfortable with.
right? So, do you have any of your tests with you or no?
I might have some. I'm not sure which ones though.
Okay, I would keep your
Let me
tests
check.
out on your desk, like in a folder.
And the practice test that we posted, a lot of the questions were like, explain how a student would solve this problem, but they didn't actually ask you to solve it. Is that like, do you think that's what it might be like?
Yeah, so they changed the test completely, right? So in the videos that I talked about that explained the changes, it's going to be like the AP1 exam instead of the APC typical exam. Like you'll have to explain the concepts instead of solving questions. So that's what they told us. So typically APC, all the questions on your tests have been questions from APC exams, previous exams. To stop kids from cheating, apparently they're moving it more conceptual, but we don't have a lot of examples of conceptual problems because that's never been how the test was formatted. So some of the questions that they're having us do as practice on that AP exam review session are questions that they just made up. So they're not previously released exam questions for the most part. Yeah, so that's why I'm having you watch those review sessions. I'm having you watch those review sessions.
Can you still use like equations to prove, like when it says verify your answer, can you still use like equations? Like, is that good enough?
You can, yes. Unless it says do not use an equation. So if you have like,
okay, so if you say like the answer is yes, and then like have equations that prove it, is that good enough for the most part?
So if we say like, let's pretend the question is, so we have an incline, right? And on the incline, we have an object rolling down it. Let's say it's a disc, right? Versus a hoop. If it asks you, to compare could ask you to compare the translational velocity. It could ask you about rotational kinetic energy. Could ask you about moment of inertia. Right, what you would do is justify in words. So let's say it asks about rotational inertia, for example. So the hoop would be more resistant to change in motion or rotation. So what you would say is the hoop has more resistance to change in rotation because the moment of inertia is larger. And you could write mr squared is greater than 1/2 mr squared.
Okay.
But you can't just write the equation. If you have no time left, writing the equation will still get you a point. But to get the full 3 points, you would need to write the hoop has more resistance to change in rotation in addition to the equation. So you want to describe the equation if it asks you to. If it uses the word justify.
Mm-hmm.
If you see the word justify, you want to use words. If it says prove, you can use equations. And only equations.
Okay. Because on the example, he barely used any equations, and it was just all words, and I don't think I would have been able to do that.
Yeah, you're not expected to do that, especially because that's not how the previous tests have gone. You can use equations to justify for APC.
Okay.
Unfortunately, it won't be as which I kind of think is unfair, but I hope that they at least give you one question that's all math. Because that's, on the previous exams, there was maybe a part D that was if this variable changes, how does the answer change?
Yeah.
But the entirety of the exam is all manipulation mathematically, and now they're create an experiment, to prove rotational momentum is conserved. And it's just like, are you kidding? I don't know. Just do the best that you can. If you have to use equations to justify, then use the equation. Just write down everything that you know.
Okay.
So you should use your note card, and I'm going to upload outlines that you can print out. But if you have your own outlines, that's almost better because then you'll know where everything is. So I would write basically common problems that you basically have had on your past AP tests. So like incline with friction, incline without friction, that kind of thing. Just so that you have a organized list of things that you can easily flip to. If time allows you to.
Do we know if one of them is going to be design an experiment?
So we know that there will be 2 questions. One of them is a quantitative to qualitative translation, which, let me head back. I don't know if you took a look at the examples from the last review session, that study guide that I posted. Those 2 questions, you did look at those?
Yeah.
Okay, so those are